right, let's go through your warm-up. All right, if I want to evaluate f of -3, which piece do I plug it into? Top or bottom? Bottom, right? Because it's less than 1. So you should have -3 plus 2. Your answer there is -1. Do I plug 2 in the top or bottom? Top, because it's a number bigger than 1. 2 times 2 plus 4. Your answer there should be 8. All good there, evaluating. Okay, so then your table. What number is going to be in this table twice? 1, and it's going to be in the middle twice. It's our breaking point. The top piece will be an open circle at 1 because we get really close to 1, but we can't equal it according to my inequality sign. The bottom piece will be a solid point when I plot it because we are allowed to equal 1. So this top part of our table is going to represent that 2x plus 4. I want to label it. And the bottom part is x plus 2. From there, really, you can pick any other numbers you want. I'm just going to keep it simple here. The top one is all numbers bigger than 1. So I'm going to put 1, 2, and 3. The bottom part is all numbers smaller than 1, so 0 and -1. And then you can just plug each of those x's into their respective equation. So if I plug 3 into the top equation, I get 10. 2, we already did that, we got 8. And 1 in, we get 6. Plug 1 in the bottom, you get 3, then 2, then 1. Okay. What shape are both of these pieces going to make? What kind of equations are those? 2x plus y equals 2x plus 4, y equals x plus 2. What are those? They're lines. They're going to be linear when we graph them. So let's plot them. 3, 10 should be up here. 2, 8. 1, 6. And 1, 6 is an open circle. And that piece is all numbers greater than 1. So that line is going to go forever to the right if it's greater than. Less than 1, 3 is a solid dot. 0, 2, -1, 1. And that equation was less than 1. So it will go forever to the left. And that's what your equation should look like graphed. Okay, so now the bottom two pieces, we need the graph to be able to answer these. It's really difficult to do these without a graph or a piecewise function. These are actually review from section 2.4, 2.5 when we did these. So f of x is a fancy way of saying what? Y. So we're given here that y equals -2. We're trying to find the x that goes with it. If you guys remember doing that, we're finding the missing part of the point. So if y is -2, I'm going to go to -2 on my y-axis. And then the graph in this case is to the left. So I'm going to go to the left about, I think it's about -4, let's say. Okay, so within a unit of that, depends how straight you do your line, is the answer. So that's the x value that would give you -2. Find the domain and range. Again, that's just from the picture. Domain is left and right. How far does this graph go left and right? Are there any restrictions? Any numbers my x cannot be? Even at 1, right, where we have the break, it's defined for one of the points. So you can list the domain in 2 different groups if you want here, or just say all real numbers. -infinity to +infinity. Remember, any domain and range you write needs to always be in this interval notation. Okay, but again, if you said -infinity to 1 with a bracket, and then union 1 with a parentheses to infinity, that is also correct. It is the exact same set of information. Range, low to high. What's the lowest this graph goes? -infinity. All the way up to what number before it jumps? 3. Would 3 be a bracket or a parentheses? Bracket. And then my union symbol, and then it jumps to what y value? 6. Would 6 be a bracket or a parentheses? And then it goes all the way up to +infinity. Okay, but those bottom two answers you have to have that graph for. It's really, really difficult to get that from the equation. Okay, this is a great problem. This is a good review of everything we've done so far in this chapter. Any questions? All right, so look at your big idea worksheet next. This is one of our parent functions actually, but I didn't assign it to any of you guys because it gets a little crazy. This is called a greatest integer function. If you were working on your Math Excel yesterday, you might have seen one that kind of looked like it had little stairs on the bottom of one of the graphs. That's what this is, okay? So the greatest integer function is a rounding function. It's a rounding down function. So if I say, and it actually kind of looks like this most of the time when we see it, I don't know, 4.8. Looks like an extra little bar on a bracket. If I see that, that means take whatever number is inside and round down to the next integer. So this would round down to what? Not 3. 4.8 is between 4 and 5, right? So rounding, it's either going to round up to 5 or round down to 4. So down to 4. Negative numbers, you just have to be careful with the negative numbers. If I said negative 4.8, what does that round down to? Negative 5, yeah. So you got to remember negative numbers. Think about a number line. If you're rounding down, you're always going to the left on the number line. So what would be to the left of negative 4.8? Negative 5. So that's what this function does. So what ends up happening when we start to graph it is any number between 0 and 1 will round down to 0, which is why we're seeing a little step there. And then any number between 1 and 2 will round to 1. And any number between 2 and 3 will round to 3. So these groups of numbers all give us this tiny little horizontal line with whatever number it rounds to. Now the left side is a solid dot because 0 rounds to itself. And the right side is an open dot because I'm at 1, that doesn't round to 0. Again, it rounds to itself. So at the integers is where it jumps to the next step. Okay. Domain is the numbers you're allowed to plug in. For this function, it is all real numbers. Negative infinity to positive infinity. The range is the numbers that are allowed to come out. The numbers that are coming out are just all those little horizontal lines, all those y values. We don't want to write those in interval notation. They are all integers. So we're just going to say all integers. Any positive or negative whole number, including 0. X-intercepts, where it touches the x-axis, there's a whole little horizontal line on the x-axis, starting at 0 with a solid dot, all the way to 1 with an open dot. Okay, so that's that little horizontal line on the x-axis. Where does it cross the y-axis? Just at 0 at the origin. It's the only place we have a point, a solid point. Symmetry, this function almost looks odd, but if you take your paper and flip it upside down, you'll notice that like this little stair here actually ends up on the left side. It ends up in a different location. That's a good place to look. So it's close to odd, but it is not odd. So we're going to say neither on this one. Neither. There are no asymptotes. Min or max values, all the horizontal lines are mins and maxes, so I don't know how you want to write this. Any line segment, I guess. Again, we're not going to list all of them because there's an infinite number of them. And then intervals, where it is increasing, decreasing, or constant. Is this function ever increasing? Is it ever decreasing? Is it ever constant? Yes, it is constant again on any line segment. It's just made up of a bunch of little constant segments, a bunch of little horizontal lines. Okay, so if you see a problem that has to do with this function on Math Excel, then that might be helpful to use this information. Okay, but this one got a little bit more involved than what I wanted you guys to worry about on your parent functions. All right. Okay, so 2.7, we're going to do a little bit, not a lot. 2.7 is about transformations. Do you guys remember in geometry taking a shape and translating or rotating or dilating? Do any of those words sound familiar, maybe? Okay, so we're going to be doing all those things, and you probably have learned these rules in some way before, but we're going to be applying them to functions now. So we're going to be taking a function and transforming it. That's the big word that's like the umbrella word that goes over all of our translations and reflections and dilations. We're transforming. These first few slides, there is nothing to write down. We're just going to kind of walk through it. These pictures are straight out of your textbook. So different transformations that we will be discussing in class. The first are your shifts, vertical and horizontal shifts, and they're showing them with different parent functions. We're going to use all the parent functions except the greatest integer one when we do this. Vertical shift is if you take the graph and just move it up or down. Okay, so we've got an absolute value graph here. If I move it up, it gets to the pink one. If I move it down, it goes to the blue one. That's a vertical shift. Horizontal shift is left and right. So I've got the blue one in the middle here. That's my x squared function. It can go left, end up there. It can go right, end up there. Is it changing the shape at all when I'm doing a shift? No, it is not. When we do a shift, all that changes is the location of the graph. Okay. The next type of transformation is reflection, which we've talked about these a lot with like our even odd functions. Reflection over the x-axis, we know what that looks like. Reflection over the y-axis, we know what that looks like. Does that change the shape of the graph if I do a reflection? It does not. It changes the location, changes the orientation, it flips it, gives me a mirror image, but the shape remains the same when we do a reflection. So we'll only be reflecting over x and y-axis. We will not be doing origin. The other transformations that we're going to talk about are vertical and horizontal stretches and compresses. Now, in the middle here, if you can see this, there's a little green cubic function. It's not the basic cubic function, but it's a cubic function. A vertical stretch pulls it. Think about taffy. We're pulling away from the x-axis, and that gives me that blue one there. Okay. A vertical shrink or compression will push it towards the x-axis, and that gives me the red one there. Is that changing the shape of my graph? Yes, it is distorting it. Think about when you take taffy and you pull it or push it, or silly putty, right? It's distorting the way that that thing looks when you do that. So that's what vertical looks like. Horizontal is going to be the same, just left and right instead of up and down. I can do a horizontal stretch left and right, and that will give me the red one. I do a horizontal compression left and right, push it towards the y-axis. That'll give me the blue one. All right. So what you need to write down, and I want you to do this on the back of your big idea worksheet, is this chart. These are all the rules that will tell us, based on what a function looks like, how has that graph transformed. The brackets here could represent any of our parent functions. So they might be a square root, and anything inside the brackets is a square root. Or they might be a parentheses squared, and everything in the parentheses, everything in the bracket is part of a squaring function. They might be absolute value bars. So the bracket part is going to change because it's going to be different parent functions we're using. But the letters and negative and positive signs based on their location are going to change the graphs the same way, no matter which parent function I have. If you have a negative outside the parent function, it's a reflection over the x-axis. If you have a negative inside your parent function, it's a reflection over the y-axis. A number multiplied out front of your parent function is a vertical stretch or shrink. It's a stretch if it's a number bigger than 1. It's a shrink if it's a number smaller than 1. A number multiplied inside your parent function is going to create a horizontal stretch or shrink. This one's a little tricky. It's stretching if it's smaller than 1, and it's shrinking if it's bigger than 1. Numbers that are added or subtracted inside are going to move us left and right. Excuse me. Numbers that are added or subtracted on the outside are going to do our vertical shifts, move us up and down. So I'll give you a couple minutes, get that written down. You're pretty much going to use this chart, this set of information for almost every single homework problem in 2-7. Okay. One thing I want you to notice here, or put a star by or something, is that our variable x doesn't have anything in front of it. And if it does have something in front of it, it's been factored out. There's a parenthesis there. You need to look before you apply any of these rules that your x variable is in the proper form. If there's a number multiplied by it, it must be factored away from the x. Otherwise, these rules will change, and you don't want to even worry about what they'll look like in the other conditions. It's easier to factor your number out. Okay, so just make a note. There's a number in front of the x, needs to be factored out. All right, so we're going to do a couple problems together up here, and then we'll get to the ones on your big idea worksheet. The first set of problems that we're going to talk about are, we have a basic parent function. Here it's labeled f of x. We have a transformed parent function, g of x, and we want to name the transformations that have occurred. So pretty much anything that's different from the top equation to the bottom equation has done something to the graph. We want to name what it does. All right, so number one thing I want to check is there anything multiplied by my x? No, so I don't have to worry about factoring anything out. Okay, next, there are three things that are different from the top to the bottom here. I have a negative in front of my square root. I have a +4 on the inside, and I have a -3 on the outside. So I'm going to name what those three things do. According to your chart, you can just flip your paper over. If you have a number in front of the parent function, what does it do? A negative in front of the parent function. Good. So we have a reflection over the x-axis. Just say reflect over x. I have a +4 inside the parent function. So if you're looking at your chart, that's a C. C is added on the inside. Now it's a positive number that's added on. So if it's a positive number added in the inside, what do we shift? Which way? We shift to the left. Now that's a little counterintuitive, okay, but we are going to go to the left is what's going to happen on that graph. And then the -3 at the end does what? Vertical shift, down 3. Those are your transformations. Let's try the next one. The next one is the cubic function, x cubed. And then I have a transformed function. Is there something multiplied by my x in this one? Yes, there is. There is a negative. So what I am going to do is I'm going to factor that negative out. Now it's important to remember that that negative is cubed. I don't want to take it outside of the cubic function because that means something different. So when I factor it out, I'm just going to create either another set of parentheses or a bracket. The negative just needs to get away from that x. If I take the negative away from the x, what am I left with inside that parentheses? If you divide it out, x minus 1, and then the whole thing in my bracket is cubed. Okay, so it's still inside the function, it's just away from the x. All right, so now let's name what our pieces do. The first piece I noticed there is I have a 1/4 multiplied on the outside. What is that going to do to my graph? A 1/4 multiplied on the outside. If it's a negative, it would be a reflection. It's a vertical stretch or shrink. Vertical shrink. And then you could say by 1/4 if you wanted to there. Second, I have a negative inside my function. What does that do? Reflect over y. I have a -1 on the inside. What does that do? Again, that's that C value. In this case, it's negative. Moves it right. How many units? 1. And then the last one, the +2 at the end. That's a D value. It's added on the outside. Up 2. Okay. Take a look at your big idea worksheet now. There are 3 of them for you guys to, 4 of them for you to practice. See what you can do. Need to factor something away from the x, do that. I need to read another way, go ahead and do that. Name the transformations on each of these, A, B, C, and D. Yes. And then we'll probably stop there for today. Okay, so mine goes A, B in the first column, C, D in the right column. So for A, you should have right 3 and up 7. For B, you should have reflect over the x-axis, vertical stretch of 3, and then in exponential functions, anything inside the exponent is considered inside the parent function. So that plus 4 moves it left 4. That's like our C value in this problem. And then the plus 2 moves it up 2. On C, this is kind of like when we did together. You have to factor the negative out. You have a vertical stretch of 2, reflection over the y-axis, right 7 because the 7 becomes negative, and then down 4. And then D is tricky when you have the rational functions, the reciprocal functions. So I rewrote it kind of like we did in that last chapter. You guys remember the U and V problem we did? Instead of 3 over x, we talked about it's 3 times 1 over x. You can think about the reciprocal functions like that. So that negative 3, I just kind of took outside of it, out of the fraction. And then I think it's a little easier to see that you have reflection over the x-axis, vertical stretch, anything in a denominator in a reciprocal function is considered inside the function. So that would be a left 1 and an up 5. So I think it's interesting. B and D have all the same type of transformations, different numbers, but all the same types, and they look very different depending on what parent function you're looking at. So you just kind of have to be careful. Those two at the bottom are definitely the trickiest, the exponential and the reciprocal, because our function looks a little different, where our variables are located at. All right, tomorrow we will finish up 2.7. Tonight, you guys need to make sure you are finishing up 2.6 Math Excel is your homework, and I'll do the cell phone model for you.